In this video then, we're going to look at scatter plots or scatter diagrams. And this is when we are plotting not just one variable, but this time two variables. So two variables on the same graph will give us a scatter plot. Okay, well let's start with a set of axes. And this time what I'm going to do is I'm going to plot the, first of all the diameter, but then also the weight of some bouncing balls. So here are our bouncing balls. And it looks as if there are 9 of them. In fact, I'm going to have 256 of these bouncing balls. So let's first of all define the objects that we're dealing with. So if we've got 256 balls, that's because I'm going to normally distribute them. In other words, I'm going to have 70 of these, but I'm going to have far fewer as they get smaller or bigger in size. So this is the average ball, if you like. So there'll be 56 of these. There'll be 28 of these. There'll be 8 of these. And only one little one and one huge one. Okay? And how huge? Well, this one is 6 millimeters. And this one is 38 millimeters. That's as big as our bouncing balls get. So the center of the most popular ball, if you like, is going to be 22 millimeters. Okay, so 256 balls, all of various sizes, but most of them averaging at a diameter of 22 millimeters. So now our first variable then is diameter. And we're going to measure that diameter in millimeters. And to give ourselves plenty of room, I'm just going to take my scale up to 40. So the center here will be 20. So we're going up in 4s. So 4, 8, 12, etc. Okay. So that's the first variable. In fact, it's the independent variable. Now the second variable we call the dependent variable. It's going to depend on what the diameter is. And the dependent variable for this graph we're going to define as weight. So we want to know what the weight of these balls, of each of the balls are. Now, weight we'll measure in grams, and we're going to assume that the heaviest ball is 100 grams. That's as heavy as any of these get. Okay, so in that case, if I go up to 50, in fact what I need to do is take it then up to this level here. So let's just erase this. So now we've got 100 grams, 50, and I think that's enough of our labelling. We can see very clearly what we've got to do now. Right, now let's first of all define what the sort of average is going to be. So this 6 meter ball here, let's just start by plotting this on our graph. Let's say that a 6 millimeter ball, so your average ball between 4 and 8 millimeters, let's say that measures that weighs 20 grams. So if this is 20 here, and this is my average ball at 6 millimeters, then I can plot this here. Diameter against weight gives me 20 grams. And let's say in this class interval here, between 36 and 40, we've got this 38 millimeter average size ball. We've only got one of those, so let's plot him at 100 grams. And all the other balls are going to go up, we would expect, in a straight line between these two. So in other words, my 22 millimeter ball is going to be plotted at 60 grams. My 18mm ball is going to be at 50 grams, and so is my well, no, at 60 grams is going to be my 26mm ball, so I'm going to plot that here. And then I've got a 14mm ball, should be here, 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 and here. Okay, so what I've done is I've defined a line that goes through my graph, and that would be if diameter and weight were absolutely aligned. So all the balls between 20 and 24, in other words 70 balls here, would be perfectly, predictably 60 grams weight. Now in the real world, of course, things don't work out quite like that. Often there's error and variation, but this would be the sort of perfect trend, if you like, a straight line going right through the middle. So let's just draw that through like that. Okay. What we'll find when we've got real data, however, is this sort of situation. If we've got weight and diameter, we would expect them to be closely correlated. Correlated means very closely connected, a strong relationship between them. But there'll be a bit of a spread. So if I think of my 70 balls in the middle here, my 70 balls that on average are 22mm in diameter, well, I'm going to expect a little bit of a spread, let's say from here to here. So some of my 22mm balls I'm only going to have measured at 50 grams. Some, very few, but some I'm going to measure at 70 grams, but most of them are going to be in the middle here. So if I plot all 70 of my balls on here now, most of them are going to be plotted over the top of each other in the center here, but some are going to go out to the edge. Most, though, centrally here. Okay, and that's my 70 plots. Now if I go to the 56 blue and the 56 light blue balls, they're in this category, this class interval and this class interval, I'm going to expect, because there are fewer balls, just a slightly smaller spread. So the most extreme is that they're going to go out like this. But these are going to be rare events. Mostly the 56 is going to concentrate around the center here, with some scattering to those extremes like that. So 56, 26mm balls, again mostly plotted in the center like that. Okay, now we move towards the edges. We've got our orange and red balls, our red and orange balls. Well, there's fewer of those, there's 28 of those, so again the spread I would expect to be a little bit smaller, so just from here to here. And there's our 28, and again smaller spread just because there are fewer of them. And there's our 28 there. Finally, we've got our 8, which we wouldn't expect to have much spread at all. Mainly going in the middle there. And finally, we've got our 2 balls here, which have measured. So we've only got 1 ball here and 1 ball here. And so we don't need to plot any spread at all. So if diameter and weight, if we've got variables like diameter and weight, which we would expect to be very closely correlated, they're clustering very, very closely, very, very strongly along this line here that we call the line of best fit. So we've got a picture here now then of what we call a strong correlation. And it's not only a strong correlation, it's a strong positive correlation. So correlation means the connection or relationship between these two variables. They're strongly correlated, so they're closely connected. And it's a strong correlation because there's hardly any spread here. It's clustering very much along this line here in a kind of thin elliptical pattern. A positive correlation means the bigger the diameter, the larger the weight. So as the diameter goes up, so the weight goes up, and the indication of a positive correlation is that we get this uphill, if you like, gradient. So we get this uphill gradient which indicates a positive correlation. So here's an example of a strong positive correlation. Now what we want to do is compare that now with a negative correlation and something a bit weaker than this, so you can see the difference. So we're going to look now for a weak negative correlation. Okay, so let's draw another set of axes. And this time what I'm going to do is I'm going to compare the diameter, just as we had before, with bounce. Okay, and to do that I'm going to start by labeling up this axis here. So I'm going to have a little break here like that, because what I want to do is record slightly different axis here, record 50mm bounce as the lowest value that I'm going to be interested in. So bounce in centimeters, let's say these are really bouncy balls. Now how high do they get? Let's go up in 20s, so this would be 70. No, let's go up in 10s. So 60, 70, 80. There we go. I can see that. So 100 would be here. So this would be 100 centimeter bounce. Okay, let's draw that a bit neater. So that's 100 centimeters. Whoops, there we go. So we've got 60, 70, 80, 90, like that. Okay, now on the x-axis we're going to keep the same variable that we had before, so diameter again in millimeters, and again we can label this up 0 to 40. So let's just finish like that. Now again, our central category is going to be really useful, so let's just label this up so we can see it very clearly to start with. So we've got 20 to 24, and then we're going to think about what our bounce would be. First though, let's just finish labeling our data. So we're going up again in 4s. Okay. And then there we are. Okay, so that's completed the labeling. Again, just the same as we had here, but now we're going to think of our bounce. Now our middle category here between 20 and 24, then let's set that as an average bounce of 70 centimeters. So here we've got the average ball bouncing at 70 centimeters high. Okay, what's going to happen then when the diameter increases? So we get our average size ball at 26 millimeters is the next class interval. So at 26 millimeters, are we going to have a bigger or a smaller bounce? So is it going to go up or down? Well, as the diameter increases, the weight will increase, as we've seen. And if the weight increases, let's say the bounce is less. So it bounces to not quite such a high level. So let's say it bounces to, on average, it bounces to 65 here. So it goes down. So as the diameter goes up, the bounce height goes down like that. Similarly, as the diameter goes down, the bounce height increases, the bounce height goes up. So now we can draw our line of best fit through these sort of perfect correlations, if you like. But as we know, this doesn't happen in practice. So what we're going to do now is simulate the spread of data, and this time what we want is a weak correlation. So let's say that we're talking about this 22mm ball here, the average size in the 20 to 24 class interval. Let's say we have a spread of, let's halve this, so a spread of 35 centimeters either side this time. So that would, 35 rather, across here, that would be too big. So we're just going to spread it 17.5 then, up to here, and down to here. So that gives us a spread for our 70 balls that are in the middle here, that are average number of balls here. So if we want to represent this, we've got to draw 70 plots now. We've already drawn 3, so we need 67 more. And again, they're going to cluster around the middle, but some of them will go towards these extremes. Mainly, however, we'll find this sort of thing happening. Mainly, they'll be going sometimes on top of each other, definitely clustering towards the center. But you can see now a little bit more the fuzzy edges that you get with a weak correlation. So we need to plot 70. Let's make sure they're scattered mainly in the middle. Something then, a few more, up to 70. Something like that. Okay, so that completes the 70 22mm balls. Let's look to the categories either side of that. So now we've got the 16 to 20 class interval, and we're going to have a spread, let's say, of 28, so 14 either side. So I'm going to just draw it at most between these 2 points here. Again, 14, so at most between here. Again, we've got to draw 56, mostly going in the middle, like this. Okay, but some scattering towards those extremes until we get 56 plots like that. Okay, and again, mostly in the middle. But sometimes outside, out towards these extremes, until we get a clear picture of our 56 26mm balls. Okay, something like that. Right, now we've done these, we've only got 28 to do here. I'm going to give that a spread then of 14, so between there and there, right, yeah, and between here and here. No, sorry, not 28, 14, 7. So it should be 7. So let's just raise that. So we don't want to spread this too much because there are half as many balls. So we just spread it. It's only going to be, in fact, from here to here, I think, to represent this smaller spread. And then we've got 28, again clustering in the middle. There you go, so clustering back there, but some coming out to those edges, so that's 28, like that. Again here, sometimes going outside, but mainly, probability is that mainly they will fall towards our line of best fit. Like that. Okay, now we've just got 8, so I'm going to just spread this 2 either side, because there's only 8 balls. And in fact we got then 3 already, so we just need to plot 5 more. So 1, 2, 3, 4, 5, and here 1, 2, 3, 4, 5. Okay, and these of course there's only 1 either side, so that completes our plotting of the 256 balls, but this time recording diameter against bounce. So what kind of correlation have we got? Well, this time it's weaker. You can see these are very tightly packed. These now are more spread out, so we'll say this is a weak correlation, and it's a weak negative correlation because as the diameter goes up, the bounce comes down. As the diameter goes down, the bounce goes up, so it's a weak negative correlation, and that's indicated by the downhill slope of the line of best fit. Okay, now finally we have these 2 plots, these 2 scatter plots, but why are they called scatter plots? They don't look scattered, the data doesn't look scattered at all. Well, the reason for that is because we've used this example, deliberately simplifying the example, so that these balls are standard diameters, if you like. So we haven't got a continuous, varying, if you like, growing bouncing ball as we're going up from the 6mm to the 38. So because it's not continuous data, that's naturally grouped it. Whereas if we had a growing ball like that, then what would happen in these class intervals is that the data wouldn't be all grouped in the center of the class interval, rather it would be spread not just up and down but also left to right in each of the class intervals. And when you do that, you get a more classic pattern, the sort of thing that you will get in real life examples when, for example, we're looking at data and experiments done with natural phenomena. So in part 2, what we'll look at to start with is a classic example of a scatter diagram using real life data where you can see very clearly this scattering effect. Okay, so here we have the example of some tree frogs. So this is a diagram showing the data gathered from an experiment involving tree frogs, and tree frogs have this unusual property apparently of, unlike ordinary frogs, they tend to hop or jump vertically rather than in a forward direction. So they, if you sort of encourage them, they will leap up and down, and you can measure the height that they leap. Okay, so on the diagram, on the scatter plot here, we've got leap height. Okay, we've got leap height on the y-axis, and we've got the weight of the frogs on the x or horizontal axis. And all the data now is scattered because this is ungrouped data. So for each value, instead of averaging it across the class interval, then it's been put exactly, in this case, at about 8.5, 8.6 to plot it against the leap height. So we get then this scatter plot, this scattering pattern across the diagram. Okay, so the problem then becomes, can we find the pattern that we saw in the diagrams in part 1? And to do that, a very good idea is to start with the line of best fit. Now, with a scattering of data like this, it's hard to see where you're going to draw that line. But the very first thing you want to say is, well, have I got any correlation whatsoever? If it's totally scattered, then there's no correlation, so it wouldn't be appropriate to draw a line of best fit. But in this example, you can see, although it's a weak correlation, there is a tendency, it seems, for there to be a downhill slant, if you like. It would be a very large ellipse, this elliptical shape that we can think about when we're looking at the data. But I think we can say that there is a correlation, a weak correlation between weight and leap height. So the first thing is to look at the data and decide is there a correlation or not. If there is a correlation, is it positive or negative? In this case it's negative, so we'd be looking to draw a line of best fit through the data here. So where exactly are we going to draw that line? Now if we use something like a pencil, that's a fairly good implement to sort of toy with. We want to do two things. We want to put it through the data, and we want to change the angle. We want to make sure we've got the angle correct, and we want to make sure that we're going right through the middle of the data. Roughly, in fact, we want to see that we've got the same number of plots above the line than below the line. And in fact, our pencil isn't going to be very good for that because it's just going to obscure lots of the plots. So it's better if you use something like a little kebab stick here and push that up through the data like that, and then position it up or down, and then angle it until you get a very, well, the best estimation of where the line of best fit is going to sit. Okay, well, failing that, you can use a transparent ruler, so let's do that. And again, with a transparent ruler you can position it very carefully so you can see whether you've got an equal number of plots above and below the line. I think this isn't quite angled correctly, and definitely it needs to go up a little, so let's just adjust it a little like that. Okay, and now we can see, yes, we have, if we count them, roughly the same number of crosses above the line that we're going to draw and below. So let's just draw the line, okay, and remove the ruler. So now we have our line of best fit. Now the next thing that we might want to do is consider the spread of the data. What we're looking for is this elliptical shape, so not just the line that goes through, but the elliptical shape that surrounds the data, and for that we need to think about where the data starts and finishes. So the beginning and end of the data, or the full spread of the data. Now we could say it starts here, but I'm not too certain that this is something we should take any notice of, because it's nowhere near the line of best fit. And I think what I'm going to do is just ignore that. Certainly to the right here, this looks much better. So I'm going to say that the end of the spread is here. So let's just draw a line like that. And the beginning, I'm going to ignore this. So I'm just going to draw a line through this plot here, like that. So now we've got a line of best fit, we've got the spread of the data, and now finally what I'm going to do is just make sure I have a clear idea of this elliptical shape. In fact, if I imagine it as a kind of fuzzy ellipse, then we can see, before we actually do any analysis on the data, what sort of pattern this is representing and where the bulk of the probability is going to lie, which is in the central region here. And what it means is that in this central region here, fairly close to that line, is where the more reliable data is going to be, because there's going to be far more going on here. As we get towards the edges, then things are going to get less reliable, and as we go beyond this elliptical shape, things are going to be unreliable, and maybe we don't even want to take any account of it. We might want to ignore this one here, for example. So these we would call outliers. Okay, so let's just get back to the line of best fit and think of a problem. So the sort of problem that we might have is, what if we had a frog? So let's call it problem A. What if we had a frog that we know is 12 gram weight, and we wanted to estimate. So we want to estimate that frog's leap height. So how high will this 12-gram frog leap, do we think? So the estimate we can get from our line of best fit. If we plot against the line of best fit, then that's going to give us the best estimate for how high the frog will jump. So we need to draw a line up to the line of best fit from the 12-gram measurement. And then we can draw along from the line of best fit to find out the expected height that the frog is going to leap. So our answer to this problem is that a 12-gram frog, a frog that weighs 12 grams, we can estimate will leap 10 centimeters. 10 centimeters. Now, of course, the frog might leap higher than 10 centimeters or lower than 10 centimeters, but this is the best estimate, and so it's the estimate against the line of best fit that they're asking us to find. Okay, what if we had a slightly different problem where they said to us, what about a leap height, a frog that leaps 2.5 centimeters. Can we estimate, so let's say 2.5 centimeters leap, can we estimate its weight? Well, this needs a little bit of thought. Again, if we think of the elliptical pattern of this data where we can reliably estimate, fairly reliably, especially as we get closer to the center, we can reliably estimate a value. Given one variable, we can estimate the other one. 2.5 is going to fall outside that pattern, and let's see how that works now. So what I'm going to do is just extend this line where the data finishes, at the beyond its spread. So let's just increase this and draw the line down to here. Now I've drawn it in red because this is a kind of danger area. We're extrapolating from the data, and it's a dangerous thing to do that. Let's have a look at the other side as well. So this was where the spread ended. So again, I'm going to draw a red line. These, if you like, are the danger areas. So if I draw now across from 2.5, then you can see it's very much in the danger area. Draw down here to, where would this be? This would be just beyond 22, so that, no, that's 26. Hang on. Okay. 28 rather. So we've got 20. We're going up in. Oh no, sorry, we are going up in 2. So I was right the first time. So that's 20 to 24. Can we say then that this frog will weigh about 24.5? 24, let's say 0.5 grams. Is that a reasonable estimate? Well, no, it isn't, because extrapolated data is notoriously unreliable. And that's because we only really know about this part of what could be not a straight line but a curve. So in other words, what you might have is, sure enough, it's a straight line here, but this might well be curving out here, so that it could weigh much more than 24, it could weigh less. This really is the unreliable part. So if we're asked, can we estimate, or if you like, should we estimate the weight of the frog, then we really would have to say not reliably. So it's unreliable beyond the data spread. And in fact, the further out we get from the center where most of the probability lies, the less reliable it gets, even out to here. Let's do one final estimation then. And this time, let's just erase this one because we're not happy with that. Okay, Let's say finally that they ask us about a 7.5 leap. That seems a bit more feasible. So 7.5 centimetre leap. Can we estimate reliably what the frog will weigh that leapt 7.5 centimetres in the air? Well, that would be to draw the line across from here, and it's within a reasonably safe part of the data, so it's here, not in the red danger area. So I'm going to draw down from here. I'm going to read off then from the weight scale here, and I'm going to say that that's 16.4 and that it's a reasonable estimate. So we're going to estimate the frog's weight at 16.4